All right, let's talk about the language of our modern world. It's not English, it's not Mandarin, it's the language of electricity.
You know, it's funny. It's one of the first things we all learn about computers. They run on ones and zeros. But have you ever really stopped to ask why? I mean, why not use all the numbers, 0 through 9, like we do? Why just 2? The answer, it turns out, is way more interesting than you'd think.
And this quote, wow, it just gets right to the heart of it. The reason computers use binary isn't some clever programming choice or a neat math trick. Nope, it's all about the messy, real-world, physical limits of electronics. The answer isn't in the code, it's in the physics.
So, to really wrap our heads around this, we have to zoom in. I mean, way, way in. Past the apps, past the code, all the way down to the single most important invention in modern history, the electronic switch.
And here it is, the transistor. The easiest way to think about it is like a microscopic light switch. But instead of your finger flipping it, a tiny electrical pulse does the job. And here's the key part. There's no dimmer. It can't be kinda on or mostly off. It is either completely on, letting electricity flow, or it's completely off, blocking it. Anything in between is just noise, totally unreliable. So what you're left with are two, and only two, super reliable, distinct states. Low voltage, which means off, and high voltage, which means on. That's it. To make it all work, engineers just gave them labels. They said, let's call the off state 0 and the on state 1. So you see, the ones and zeros we always talk about, they're just nicknames for the physical state of a tiny switch.
Okay, so one switch can be a 0 or a 1. Big deal, right? That's not very useful by itself. But what happens when we start putting these little switches together in groups? Well, that's when things start to get really interesting.
Each one of those little on or off switches, each 1 or 0, has a name. It's called a bit, which is just short for binary digit. Think of it as the single atom of digital information. And just like atoms, one bit by itself can't do much. The real power comes when you start combining them.
And this is where you really see the magic of exponential growth. With one bit, you have two choices, 0 or 1. But add a second bit, and now you have 4 possible combos, 0, 0, 0, 1, 1, 0, and 1, 1. Add a third, you get 8. A fourth gives you 16. Every single bit you add doubles the amount of stuff you can represent. It gets big, fast. Now, pretty early on, engineers decided they needed a standard-sized chunk to work with. So they grouped 8 bits together and called it a byte. With 8 bits, you suddenly have 256 different possible patterns of ones and zeros. This became the workhorse of computing, used for everything from representing a letter of the alphabet to a shade of color on your screen. So how does a computer actually count with this? Well, we use a base 10 system, right? The ones place, the tens place, the hundreds place, all powers of 10. Computers just use base 2. So they have a ones place, a twos place, a fours place, an eights place, and so on. So for the binary number 0, 1, 0, 1, you just add it up. There's a 1 in the fours place and a 1 in the ones place. 4 plus 1 is 5. See? It's just a different way of counting, one that's perfect for a machine that only knows on and off.
Okay, so storing numbers is cool, but a calculator just stores numbers. A computer needs to compute. It has to make decisions. And it does this by arranging its little transistor switches into tiny, simple, decision-making circuits.
These little circuits are called logic gates. All they do is take in a couple of bits, look at them, and then spit out a single bit as an answer based on a very simple rule. These are the absolute most basic brain cells of a computer.
Let's meet a couple of them. First up, we have the AND gate. I like to call this one the strict one. It is a real stickler. It will only, and I mean only, output a 1 if all of its inputs are also 1. If even one input is a 0, the answer is 0. No exceptions.
You can see it right here in what's called a truth table. Just look at that output column, 0, 0, 0. There's only one way, one single combination that gets you a 1 at the end. Input A and input B have to be 1.
All right, now let's meet its much more easygoing cousin, the OR gate. This one is the inclusive one. It's way easier to please. It will happily give you a 1 as an output if input A is a 1 or if input B is a 1. It doesn't need both.
And its truth table shows you just how chill it is. Look, the only way you get a 0 out of an OR gate is if everything you give it is a 0. Any little hint of a 1 going in, and you get a 1 coming out. And believe it or not,
By combining millions and billions of these incredibly simple AND and OR gates, computers can perform all the complex logic and math they do.
So let's recap. We have tiny transistors acting as on-off switches. We use those switches to represent bits, ones and zeros. Then we arrange those bits into logic gates to make super simple decisions. So, how do we get from that all the way to watching videos and taking selfies?
The answer is one of the most brilliant ideas in all of computer science: layers of abstraction. Think of it like this. At the very bottom, in the basement, you have the physical transistors. They're used to build the logic gates on the next floor up. Those logic gates are then used to run machine code, which is created from the high-level code that programmers write. And all of it, is hidden way below the beautiful user interface that you actually see and touch. Each layer only has to worry about the layer directly below it, hiding all that insane complexity.
And what is all this incredible layered machinery actually doing at the end of the day? It's just shuffling numbers around. That's it. Every letter you're reading right now is stored as a number, using a code called ASCII. The photo you took is just a huge grid of pixels, and each pixel's color is defined by 3 numbers. One for red, one for green, and one for blue. It's all just numbers, which are really just patterns of on and off switches.
The secret sauce that makes this whole thing work, that takes it from a simple concept to a world-changing technology, is scale. A scale that is almost impossible to comprehend. On a single tiny chip in a modern computer, you can find more than 15 billion of those little transistor switches, each one flipping on and off billions of times every second.
So, when you peel it all back, you get to this one simple, beautiful truth. We aren't really running apps on some magical box. All the amazing complexity of our digital lives simply emerges from electricity, controlled by incredibly simple rules of logic, happening at a mind-boggling scale.
Which of course leaves us with one last big question. We have built our entire modern civilization on the simple, reliable difference between on and off, and it really makes you wonder, if this is what we managed to build from a simple switch, what's next? What will be the building block of tomorrow's world?